Hello everyone, welcome to a new video in Harsh IT Lab in which we are going to discuss IPv4 addressing. We have come so far now, but before addressing the today's topic, first I want to discuss about the Cisco device itself, starting from the mere basic of a Cisco device. For example, a router or switch. The number of operational port depends entirely on the model. But some things remains common on all of the Cisco device is presence of a USB port, a console port, and a power on off switch. Talking of console port, we have already learned that to connect with console port we need to use a rollover cable. The one end of rollover cable goes into the console port itself while the other end goes into a DB9 or DB25 adapter. The DB9 adapter enables the communication of the rollover cable to PC through COM port. COM port stands for communication port. COM ports are the legacy interface used in computers in earlier times and are now obsolete due to its slow speed. But still, for computer having those, we can use those ports to configure our Cisco device, while the other DB25 adapter helps to connect the rollover cable to a PC using serial port. Enough talking about physical connection. Now let's talk about the commands hierarchy on a Cisco device. Now let's talk about the software running on a Cisco device itself. iOS, not the Apple iPhones one, but Cisco devices like router and switch also runs the iOS on them. Depending on the part number, some features varies on a switch. For example, if the part number contains the word K9, it means that the switch is enabled with cryptographic features like SSH, HTTPS, etc. Despite having differences, some things are common in them. Let's discuss them in detail. As a security feature, Cisco iOS software separates the executable sessions into two different access levels. The first, smaller level, in which very few commands like ping or viewing command configuration are available, is called user exec level, while the other, more advanced version with higher sets of available command is privilege access level. We use user exec level commands to enable or enter into privilege access level by issuing the command enable. All the user exec commands are available in privilege access mode with inclusion of debugging commands, reloading, configuration commands. There are much more command available. You can view the all available commands in any mode by issuing a question mark. You don't need to press enter. Privilege exec label allows a user to change the configuration of the device by entering into configuration mode. There are 5 configuration mode available on a Cisco device. The 5 modes are global configuration mode, interface configuration mode, sub-interface configuration mode, router configuration mode, and the line configuration mode. Sub-interfaces are logical and virtually created interface used to make routing decisions or checking stuff. Interface configuration and sub-interface configuration commands used to change the parameter of the interface itself, while global configuration modes allows us to do basic configuration like the hostname change, enabling password, or modifying the IP address table of a router. Router configuration mode enables us to change the values of the protocols enabled to make the routing decisions like RIP, OSPF, IGRP, etc. that we will study in our further video. And finally, the line configuration mode enables to modify the parameters of physical as well as virtual out of band management interface or ports. Until now, we have discussed the physical availability of the ports on a Cisco device and the hierarchy of its operating system. Now it's time to discuss what kind of storage options are inside a Cisco device. After this, we will also discuss about the file system of a Cisco device. Starting from mere basis, on a Cisco device there are four main memory area. The first is RAM, second is ROM, third is flash memory, and finally the NVRAM, which is non-volatile RAM. Being an IT geek myself, I am sure that everyone's know what a RAM and ROM does in a system, and some of us also know what the flash storage means. For those who don't, the RAM stores the currently working task. For example, for a computer, the current opened program performs its function in RAM because RAM is the fastest kind of memory available in the computer. It is also referred as system memory but has a drawback that it loses its content whenever a device is restarted. Second is ROM. ROM stands for read only memory, which means it once written in cannot be changed, or to change this someone needs a specialized hardware, and due to the same difficulty or the inability to change at the moment, it is best suitable for storing the information of POST. POST stands for Power On Self Test or the bootstrap program. You can refer this as the BIOS of a computer, which enables the starting of main operating system. And now we are going to talk about flash memory. I bet that you have seen a pen drive or a SD card. These are all form of flash memory. Even the newer latest generation SSDs are some sort of flash memory. On a Cisco device, the iOS software, that is the operating system of a Cisco device, is stored along with some other files like backup and configuration. Flash memory is infamously the cheapest available memory, or in other words, it is the memory that is present in higher quantity or amount on a device. Now, time to address the elephant in the room, NVRAM. Out of every mock session that I've attended during my preparation, there is always a question that where the Cisco routers store its startup configuration. By configuration, I means that the all the static information that we want the router to keep in its memory before deciding how to route a packet, as we want some information to be in memory even after the router gets restarted or not. We have to manually save it by issuing a write command. But where does the saved data goes? The answer is it goes in NVRAM. If I remember correctly, I have already told that NVRAM stands for non-volatile random access memory, which means it possesses the best of both worlds. Like non-volatile, it is not erasable, while random access memory means it is faster than the flash, which enables a device to make its decision quickly as soon as the packet arrives. After learning all these things, it seems like router or switch is just like our computer. So, can you think, is there likely a possibility of having a CPU in it? If your answer is yes, then yes, you are absolutely right. There's a CPU in a Cisco device as well. I am already pretty bugged with a Snapdragon 400 series CPU on my smartphone and a i3 CPU on my laptop. It's slow. So I have always wondered how a router or a switch can handle gazillions of packets simultaneously passing through it at once. And the answer is that routers or switch use a special chip called network processor to process routing packets much more efficient than a CPU can. The network processors are designed to handle the complex task of packet processing, packet classification, queuing, scheduling, while the CPU in a router executes the command and processes the command in the operating system, iOS for Cisco or Junos OS for Juniper devices. The CPU controls the flow of data on the interface and is responsible for routing protocols which are used to determine the path for packet. As further we are going to discuss about routing protocols, beware that using too much routing protocols may slow down the CPU and the overall operation of the Cisco router. But to better classify what a router or switch does, we use the term plane. The term plane refers to the logical surface or process of defining how data goes out and processed by different logics. For the purpose of classification, there are three kinds of plane exist on a networking device. First is control plane, second is data plane, and finally the management plane. The easiest of in all three planes is the data plane. The data plane is something which has the forwarding information. For example, the network packet sent from a device to another one device is considered to be the part of data plane. It takes the help of routing table or any other access rule to define how the traffic is to be handled and based on which interface it entered and how it goes out of the router. While the traffic destined to the router itself, for example, the out of band management traffic that we have just learned, the traffic coming from the console port is termed in control plane, and the last remaining plane, the management plane, is a subcomponent of control plane because management plane can be controlled by control plane. The management plane features the inbuilt installed functions on a Cisco device or a networking device which used to edit, monitor, or manage the device and its working itself. For example, the command line or the graphic interface are the components of management plane. It's been a while talking about the Cisco device and its feature, function, its components. Now it's time for the main topic, which is IPv4 addressing in this recording. IPv4, which is an abbreviation of Internet Protocol version 4. The Internet Protocol is a protocol or set of rules for routing and addressing packets across the network so they arrive at the correct destination. The data traveling across the internet is divided into smaller pieces known as packets. In the previous notes, we have already learned that packet is the special name for layer 3 PDU. So it's all pretty clear that we are now in the layer 3 of OSI model and the IP information is attached to each packet and this information helps router to able to send packet to the right place. And how it does so? By assigning an unique IP address which is a 32-bit or a 4-byte field separated in 4 octet with dot in between. And with the 32-bit limitation, when we raise 2 to the power of 32, we get something of an average of 4 billion addresses. And with the rising number of internet devices, this has quickly become the limiting factor of possible assigned device. So to address this very big problem, we have developed the IPv6, the 128-bit addressing scheme. Although it is not widely accepted as the legacy devices which cost too much to replace supports only IPv4. So this is a compulsion for network engineers that they can only implement IPv6 only if they are starting from the foundation. So what to do now if we are stuck with IPv4? So we have also developed some another special techniques to preserve the remaining IPv4 addresses like categorizing the address. The classes of IP address were created by IANA, which stands for Internet Assigned Number Authority. The 5 classes of IPv4 addresses are A, B, C, D, E. The devices on internet uses the first 3 class that is A, B, and C, while the D and E classes are reserved for a special purpose. The class D addresses are used for multicasting and stuff, while the class E addresses are reserved for research and experimental purposes. Within the A, B, and C classes, there are further reservation of few selected IP addresses for the internal routing, that is within the LAN, not concerning with the external internet. Such routing or such network addresses is called private IP address. I will shed the light on private IP addresses soon after we talk about subnetting. Subnetting is pretty self-explanatory topic in itself. By the name, we can assume that we are going to divide the network in subsections. To start from start, we know that IP address is of 32 bits and every bit is either 0 or 1 as the computer understands binary form, and those 32 bits are divided into 4 sets of octet. For every octet there is 8 bit, and the sum of the octet represents a value between 0 and 255. Therefore, the total IP range ranges from 0.0.0.0 to 255.255.255.255. And to make the networking more feasible, these IP addresses are divided into two parts. Some values of an IP address represent a network ID, while the remaining one represent the host ID. When we write the IP addresses in binary form, the subsequent ones on the left hand side not only but mostly represents the network ID field, and after we take out the network ID, the remaining zeros and ones are called host ID. When it is said to write the network ID of a IP address, we fill the host ID with zeros in it. Complete IP address. The host ID represents the uniqueness of a device into a network, while the network ID represents the location of the device and its peers. If you have listened with full concentration, I'm sure that you have noticed that I said there may or may not be a subsequent number of ones in the left hand side representing the network ID. What will happen if the host ID also contains the letter 1 in its the leftmost part? Then I'm sure that we will get confused whether network ID extends to 7th digit or the 8th digit or the 9th digit. So is there a certain way to make this certain that up to this digit it is network part while the other is host part? The answer is subnet mask. Subnet mask is just like IP address, a 32-bit field which contains either 0 or 1, but when kept in parallel with IP address, the ones in subnet address represent the network portion, while the zeros in subnet address represent host portion. Having a subnet address makes the identification easier of host and network portion, as it explicitly contrasts between network and host portion. Not only humans but router or switch also use the subnet IDs to get information about the network. So we can say the subnet is a tool, and by using this tool we do something known as subnetting, in which we explicitly define up to what range a router can route packets in a network. Talking about subnetting in audio format is a very tedious task because it leaves room for confusion. So I will make a video on this in soon coming future. But a thing that I want to make you remember that the one in the most right part of a subnet represents the increment of a network, and within each subnet the first and last IP address are non-usable. as the first IP address is the network address itself, while the last IP address is known as broadcast address for the subnet. And after writing the subnet in decimal form, when we find the value of the rightmost one in subnet, it defines the increment of the subnet in the respective octet. To get this point better, don't forget to watch my subnetting video, which will be my upcoming video in next few days. Now the time has come to talk about public and private IP address. The public IP address is the most simplest to explain. It is an internet address that can be accessed over the internet and is assigned by RIR. RIR stands for Regional Internet Registries, which assigns the IP address depending on their region. We have already discussed that giving or assigning a unique IP address to every device is not a feasible option because we have only so many addresses. So what we do is to use private IP address. So the private IP address is a type of address that a router assigns to different devices on a network, which is used to communicate between devices through router. And to send the traffic to internet, the addresses needs to be translated into a public IP address first. The translation part is also in our syllabus which we are going to study, but not in this video. That's a topic for another day. Now you have also heard the term static IP and dynamic IP addresses. These are nothing special but the fancy name given to type of addresses that change from time to time or doesn't change at all. The name explains itself. The static means fixed or that does not move. So the static IP addresses does not change as during the network management we want some addresses to retain while it is not viable to assign a IP address to each of the device. So we want to automate some tasks. For the automation, we use another protocol called DHCP, which again we are going to talk about in future video. But it is our task of assigning IP address, and the IP addresses which assigned by DHCP is dynamic, which means it can change from time to time. Enough talking about IPv4 addresses. Now it's time for to talk about IPv6 addresses. Most of things applies to both kind of address similarly, but the categorization of addresses differs. The category or types of IPv6 addresses present are global unicast, unique local, loopback, unspecified, embedded, link local, well-known multicast, solicited node multicast addresses. Don't get scared by all these names. As soon as we start discussing the terms, I will tell you the equivalent IPv4 term. So that will make a lot easier to digest. And just by summarizing these terms, we will also see some new additions to our IPv4 information. Starting from global unicast, just like public IPv4 addresses that are routable on interface and is unique on per device basis, the global unicast addresses are the same, but for IPv6, IPv4 addresses are made with some bits of network ID and the remaining bits of host ID, while the IPv6 addresses are made up with some bits of global routing prefix, then some bits of subnet identifier, and finally the host portion. The global routing prefix is the fixed value allocated by IANA, Internet Assigned Number Authority, depending on the region you live, while the subnet ID can be configured by administrator or internet provider to create subsection of the network, while the host portion identifies each unique host on the network. The global routing prefix is of 48-bit, while the subnet ID is of 16-bit, and the remaining 64-bit is known as interface ID or the host portion. And just like the private IP addresses space in IPv4, we have unique local addresses in IPv6. These network addresses can be used without the need of registration to an authority. However, FC00 or you can say FC00 are reserved for the first 7 bit of IPv6 address. After the reservation, only 41 bits are left for global ID, which is usually identified or assigned by internet provider, 16-bit for subnet ID, and finally the remaining 64-bit is for interface ID, that is host portion. Now it's time to discuss link local addresses. The link local addresses is auto-configured address on an interface with combination of link local prefix, that is FE80/10, and the MAC address of the interface. The idea behind link local address is to enable the communication or a common link without the need for globally unique address. This address has very limited scope, which means that router do not forward the packet that have a link local source or destination to other link. It only works between two networking devices, not more than that, not less than that. Link local addresses are used in point-to-point communication and helpful in neighbor discovery, as the IP version 6 does not use ARP, address resolution protocol, as it comes baked with feature like NDP, network discovery protocol, which reliably helps to find neighbors within a subnet. Now it's time to discuss loopback addresses. It seems like I have forgot to discuss loopback in IPv4, but IPv4 and IPv6 loopback address are essentially the same. The loopback address is merely a logical interface that has no physical representation and is always up and running. The packets sent to a loopback addresses are returned on the same interface. Within the class A of IPv4 addressing scheme, the network 127.0.0.0 contains all the loopback addresses. These addresses are used for testing purposes as they are never down. Loopback addresses are also known as localhost in various operating systems. The main difference between IPv4 loopback and IPv6 loopback that we have a complete network decided or designed only for loopback purpose in IPv4, while there is a single address that is 0:0:0:0:0:0:1 as loopback interface in IP version 6, which can be shortened into double colon 1. The shortening of IPv6 addresses is an essential skill for network engineer. I do recommend to watch Jeremy's IT lab shortening video as well as some other resource which you can find on internet, and if you lean I will make a video on that topic also. Now the next topic is unspecified address. This is pretty self-explanatory that if I want to send something but I don't know the address, we will leave the address space blank. That is, the every bit is 0. For IP addresses in version 4, every 32-bit is 0 is termed as unspecified network address, and the same 128 bits and every each bit is turned 0 is an unspecified IPv6 address. Now it's time for embedded IPv4 in IPv6 address. I have already told you that not every device is IP version 6 ready. So to compensate the transition, there is a method of embedding the IPv4 addresses in an IPv6 space. We can do this by filling the rightmost 32 bits with IPv4 addresses. But one thing must be taken care of, that IPv4 addresses are written in binary while the IPv6 addresses are written in hexadecimal. So before embedding it in IPv6, we have to convert the IPv4 into hexadecimal. In the same video of Jeremy's IT lab, it is explained how to convert between these two types of notations. During IPv4 talk, I have briefly picked about broadcast address. The broadcast address is a type of address on which, when a packet is sent, it is shared or sent to all hosts in that subnet. I am making it clear here that there is nothing as broadcast address in IPv6. In IPv6, we have multicast addresses. The multicast and broadcast has a major difference in it. The relationship between multicast, sender and receiver, is just like a YouTuber and its viewer, the relationship of subscribership. The receiver who subscribe to the multicast will only receive the packets, as the packet sent to a multicast group always has a unicast source address. Unicast means the packet projected to a single receiver. All the host addresses that we talked in IPv4, even in IPv6, are the unicast addresses, means it points to a single host on the network. Another point is that a multicast address cannot be a source address of a packet, as it would create ambiguity, which means that multiple devices can be associated with the same address. So the receiving device would not be able to identify the specific sender or respond to the sender correctly. So who are the subscriber of multicast? The answer is that the protocols like OSPF, EIGRP, VRRP, which we will be going to discuss in detail, subscribe to their specific multicast address to listens for the neighbor. However, all the nodes on the network subscribe to the multicast FF02 double colon 1, while all the routers on a network subscribe to multicast FF02 double colon 2. There's a list of these types of values which you can find by just searching IPv6 multicast addresses. This list must be remembered as it is a topic listed in CCNA examination, in which we can also find that multicast addresses for OSPF, EIGRP, PIM, VRRP, and much more. Now there's another form of multicast that is used for address resolution, network discovery, and duplicate address detection. That form of multicast addresses is known as solicited node multicast address. It is automatically generated from the IP version 6 unicast address, as the solicited node multicast address are made up with MAC addresses. We can see it closely resembles to an ARP request, the address resolution protocol request, which is a request sent by a device to know IP address associated with the device, to know MAC address associated with the IPv4 address to a device. So, right before wrapping this video, I want to tell you about how the network discovery protocol in IPv6 works, which is just equivalent of ARP protocol, address resolution protocol. Suppose a device wants to send a packet to another node on the same link. It first need to determine the link address of the destination node. By link address, I mean the MAC address or the link layer address or the data link layer address. Enough synonyms. Now, to do this, the node or the device sends a neighbor solicitation message to the solicited node multicast address of the destination node. The neighbor solicitation message contains the IPv6 address of the target, and the destination node responds with a neighbor advertisement message which contains the MAC address of that specified target. And after receiving the network advertisement, the device places the MAC address in their table for future use. Apart from neighbor solicitation and neighbor advertisement message, network discovery protocol also use two special messages called router solicitation and router advertisement. Router solicitation is the demand of a node for getting the default gateway address prefix information, while the demand sent by a router contains in router advertisement. I hope you are satisfied with this video. I would be happy if you comment the shortcomings or criticism of these notes. Thank you.